Thank you to everyone for coming. My name is Marcus Schwarting. I am the senior editor of the editorial team of AI and Faith. So a bit about my background here. I did my bachelor's at University of Louisville. I have worked at Argonne National Laboratory and the National Renewable Energy Laboratory for some time. And I'm currently doing my PhD at the University of Chicago. My work is endowed by 3M Company. And my work mainly cycles around AI applied to cheminformatics and materials science, but also been quite involved with the large language models over the last few years. So here's a quick overview of the talk. I'm going to start with some motivations here, go through a basis of deep learning, some of natural language processing and the current transformers we've been seeing, and then how those transformers end up misbehaving, and other concerns around adversarial machine learning and data. So starting with motivations, I think my biggest point here would be that AI and Faith really ought to focus its efforts on some of these legitimate ethical concerns of large language models, or else if we don't end up doing that, it can be a risk to our credibility. I think a little technical knowledge in this aspect can go quite a long way. And I would highlight too that large language models are here to stay. They're powerful. I don't think it's all just hype, although there's certainly been a lot of hype around them. And as AI ethicists, I think that we ought to maybe invest in some of these technical basics in the same sort of way that bioethicists are expected to know some of the principles of medicine when they're adjudicating various decisions. So first, let's talk about some of the basics of deep learning that really undergirds these systems. And for folks who are on the technical side, this may be a bit of a review, so maybe bear with me here for a second. So this all started in the 1950s with the invention of the perceptron. And the idea here is that it's a partial substitute for a biological neuron. So we have a neuron here on the left, and we have these dendrites that are receiving electrical signals in our brains, and based on various chemical pathways are firing an electrical signal down to these synapses, which are passing a message effectively to surrounding dendrites and surrounding neurons. Now the perceptron, introduced by Rosenblatt, does essentially the same thing, only using vectors and matrices and combining various weights. You're essentially taking in your surroundings in all of these numbers here, you're applying some function, and then you're passing on a signal. So the next step really came when we started combining these perceptrons in various layers. So we start out with an input set. This could be just about anything associated with numbers here. And we end up passing these through what we call hidden layers. And these hidden layers are iteratively transforming inputs again and again and again until we reach an output layer. I'm not really going to talk about how these systems are trained, but suffice to say that we can train them quite robustly. And then starting to get towards the specifics of how these large language models are working, they are within this class of recurrent neural network architectures, which is similar to the baseline neural network, except it is constructed to make predictions in a sequential or time series type of fashion. So they're frequently used in stock market forecasting and quantitative trading, but they're also the basis of the large language models we're seeing today, which are essentially, as we'll talk about, iterating to predict the next word in a sequence. Okay, so now diving more into the specifics of NLP and these transformers we're seeing now. So two important concepts to keep in mind here. The first is that words are interpreted as vectors, as a set of numbers. So one way to do that is a process called tokenization. So you could think of taking every word in the English language and just substituting it for a specific number. However, that doesn't really capture any sort of information about how language is actually semantically, how it semantically occurs. And to do that, we use embeddings. So an embedding is a unique vector for each word, which through various mathematical procedures is embedded with contextual or semantic information about the word, at least relative to other words. So around 2013, this model called word2vec came out. And this is a fairly intuitive optimization process. It relies on some linear algebra that we won't get into. But by embedding these words in this space, you'll see on the right here that, for example, I am clustering words that are semantically similar, like animals here, and cat and kitten are closer to one another than dog, and all of them are quite far away from houses, for example. Embeddings also let you do some interesting math with these representations. So for example, in this latter example, we see that if I take the embeddings for king plus woman minus man, I end up with queen. So there's actually some semantic quote unquote understanding going on here based on this process. And so that's one of the key portions of how these large language models work. The other is what's called an attention mechanism. So recurrent neural networks struggled for quite a while with assessing the importance of particular words in a particular context. And so this attention mechanism developed around 5 or 6 years ago is meant to iteratively assign words importance relative to one another. So these attention-based systems are really 3 steps. The first is I create an embedding, which we just talked about. The second is I have this sense of system memory here, which is essentially aggregating the distribution of past embeddings and giving this sense of attention, this relative memory of how important other words are versus each other. There's some other math that goes on here, and then we are sequentially assessing what that next embedding ought to be for my next word prediction. And so in the last couple of years, the last 6 months, this has all sort of come to a head, but you all have essentially seen the basics of what's going on with these systems. In the last couple of years, what you've really seen is that we've increased the size of the models and the scalability, and we've made improvements for how they are trained. But the essential components are what we have just discussed. And in terms of making these models larger and larger and larger, it really remains unclear when we can start expecting to see diminishing returns based on size. That's sort of an interesting question we could dig into later. And, I would point out here that from a linguistic perspective, language is stochastic. And what I mean there is a deterministic system is one in which, well, for a given input, my output is always the same. So there are plenty of deterministic models out there. They predict an outcome with essentially absolute certainty. Stochasticity is the opposite of that. So for a given set input, my output can change. And no matter how much information my input contains, the output is never 100% certain. So stochastic models, like large language models, are predicting multiple outcomes with varying certainty. And I would argue that language is stochastic, and this isn't a bug, this is really a feature. So if we think of this example of predicting the next 2 words in a sequence, Mary had a blank blank, we might be inclined to say little lamb, but this problem has many answers, and it depends on lots of factors like context and many others. And so thinking of transformers just in terms of their inputs and outputs, my input here for the problem, Mary had a blank blank, is my matrix representation of quote unquote memory. That's the attention portion. And then there are the embeddings of the immediately preceding characters. In this case, we just picked the last 2, had and a. Then we run what's called inference, where we're essentially passing this information through that neural network. And what we get out is a set of likelihoods associated with that next possible word. So they are in the form of these embeddings, and they are the most likely following characters in this statement. So we see that little has a large percentage, the largest percentage, and so we take that word. But there are others that we could choose as well that might make sense in that context. And so iterating again, we have this word little. Now our inputs have changed a little bit. our matrix representation of memory now includes that word little, and the embeddings of the immediately preceding characters, in this case, the previous two, are now a and little. So I run inference again, I pass it through my neural network, and I get this stochastic output, in which case I get the word lamb. But I also get other words that could be in place and also sensible. And by the way, this is why OpenAI charges by the word. This process of transformer inference is somewhat expensive, and that's what OpenAI is charging you to do. So now that we've talked about how they work, let's talk about how they don't work. So one area that maybe you've heard recently is this idea of ChatGPT versus Google. The common frame here is that you can think of large language models as iteratively predicting, generating the next word in a sequence. So when we're talking about a problem of retrieval, the way Google does, we're talking about fetching data that's relevant to a particular query. And it should be noted that when I'm retrieving something, correct attribution is implicit because I give you my sources. There are already really popular retrieval methods, some of which have properties of natural language processing in them, but they're extremely effective and efficient. So I would argue that large language models are actually a poor substitute if what you're really doing is retrieval. And as we talked about, large language models are stochastic, the way language is stochastic. So the attributions that a large language model would make are also going to be stochastic. So really, I would argue that large language models, they're not designed to perform retrieval. And the accuracy relative to the source is not guaranteed because this is a probabilistic system. The other thing that folks talk about quite a bit is how to correct a large language model's behavior. Again, we are iteratively predicting the next word in a sequence. So you might hear folks ask, why don't we just force large language models to cite trustworthy sources or not say something violent, or even just refuse to answer certain questions? If I ask it how to build an atom bomb, it probably shouldn't return an answer. So for these models, quote unquote, correct behavior is solely a product of the higher probabilities I weight towards given words for the next prediction. That's what's meant to constitute proper behavior as far as we can control it. So really, this notion of correct or proper behavior, no matter the situation, is not guaranteed. And the system just guarantees that it never will be a guarantee, if that makes sense. That was a little wordy. So how can we alter the performance of large language models? So really, there's only a few tools available that allow us to correct this behavior. The first and most talked about is this idea of fine-tuning. So essentially, I have a large language model that I take off the shelf from OpenAI or another place. This is pre-trained on a specific corpus. That specific corpus, we sometimes call it the pile, which is just all the data that's been scraped off the internet, essentially. And I forced it to change how I weight certain next word predictions based on some particular corpus. Now, the corpus that I supply for fine tuning is ultimately what differentiates my LLM from everyone else's. So if you're out there fine tuning a large language model, pick your data carefully. And I would stress that anyone can fine tune an LLM with some fairly basic technical knowledge. And depending on the size of the fine tuning corpus you're using and the model architecture you pick, you can expect to spend anywhere from 10 to $500. It's really not that pricey, and our group does it quite frequently. I've done it frequently too. One example of how this fine-tuning might work is in the pre-trained model. What you get off of the shelf here might say Donald Trump is and then the next word is politician or businessman or something else. But when I fine tune with data from conservative US media, it's going to have a more favorable impression, a less balanced perspective, you might say. And it would say that Donald Trump is a hero or a genius or something else. So someone might say, I have a GTT model that returns XYZ, but if they don't tell you what their fine tuning data is, you can't really understand how it's going to perform. So a certain type of fine tuning that people have used quite frequently is RLHF. That stands for reinforcement learning with human feedback. And this idea is that humans are going to query the LLM in lots of different ways and either make scores or corrections based on what the LLM returns. Those interactions you can think of as a collected corpus, which you can use for fine tuning. So reinforcement learning is kind of it's a separate branch of AI with its own set of problems. And one of those problems is that reward functions are notoriously hard to assess and calibrate. And it really requires a tremendous amount of human interaction before clear differences are observed. So GPT-4 comes with some of that RLHF baked into it. And it's really not clear just how many resources OpenAI dedicated to this human-based processes, but it was a lot. You really need a lot of data in order to move the needle. So a couple of terms that you'll hear quite a bit is zero-shot and few-shot learning. So zero-shot learning is, I'm not quite sure why people call it learning at all, because it means that I didn't do any fine-tuning. I just queried the LLM and I am giving you what it output. Maybe I have some specific intention in mind, but zero-shot learning usually leads to few-shot learning. And this is this idea of fine-tuning or RLHF on a quote-unquote small corpus. And small here is sort of in the eye of the beholder, but typically it's much less than the size of what's been scraped from the internet. That's quite a bit of data. The final technique for correcting the behavior of large language models is what I like to call circuit breakers. That's not what it's called in the literature. It goes by lots of different names. But essentially what's going on here is, as my large language model is processing that next word prediction, as it's passing through each of the layers in my neural network, I can stop at an intermediate state and I can look at what's going on. And I can assess either on the input side, did the user ask for something inappropriate? Or on the output side, will this model, is it about to generate something inappropriate? And I can break in and stop that from happening. Paradoxically enough, some of the best circuit breakers are actually large language models that are designed to classify content as being violent or non-violent and whether or not to interrupt that process. If you've been playing around with ChatGPT, you'll know when you've hit one of these circuit breakers when it says something along the lines of, as an AI model, I am not permitted to say XYZ. Or most recently, if you ask it something like how to build an atom bomb, it will actually return, I'm not comfortable with this conversation, and it will leave. You won't be able to query it anymore. You'll have to start a new session. So unfortunately, if I do fine tuning or RLHF in conjunction with these circuit breakers, I can actually end up changing that latent state and breaking my circuit breakers. So that's been quite an issue as of late as well. So now let's talk about some of the adversarial approaches that people are already trying here. So adversarial machine learning is this area where I take a trained model and I try and break it in lots of different ways. And it's been a growing area for quite some time, but researchers in this area are demonstrating how large language models can be used in lots of potentially harmful ways. The first and maybe clearest understood is this idea of adversarial prompt engineering. That's what you see on the right here, where you sort of sucker the AI into saying something it's not supposed to say. Maybe you all have played around with that and have even gotten your LLMs to say something it maybe wasn't supposed to say. And there's this idea of reverse feature hashing. This is kind of this idea of looking at the hidden states and breaking your circuit breakers through fine tuning, getting it to promote explicitly sexual content, for example. Then there's this idea of membership inference. So let's say I trained a large language model with some sort of personally identifiable data like medical records. Membership inference is the process of querying my model until I figure out some specific piece of information about whether or not that say medical record was a part of the training data or not. And depending on the sensitivity of that data, it can be a pretty powerful attack. There's also this idea of knowledge distillation or weight stealing. OpenAI is currently suing some folks for doing exactly this, essentially making an open source copy of their model that's more lightweight and is capable of doing essentially not identical performance, but very similar performance. The last two that I think people are worried about on the horizon are large language models being used to automate attacks on cyber infrastructure, really trying to brute force into breaking API interfaces, making API calls, that sort of thing. And then large language models have also been used recently as for encryption. Some really interesting cases there that we'll see how those bear out. But essentially, you can hide a coded message in text that looks perfectly reasonable and innocuous. So regarding privacy and data concerns, if you're fine-tuning an LLM through one of these paid services like OpenAI, you should know that OpenAI is essentially involved at every step of the process. They're collecting every query you submit and every output that's recorded. OpenAI is capturing all the data that you supply for fine tuning. So you should never supply OpenAI with data that has some sort of embargo or sensitivity associated with it. This could be exposed by a leak or by adversarial ML, or you just might not want OpenAI to have it. OpenAI is going to charge you by the token for both querying and fine tuning. And OpenAI keeps your fine-tuned model at the end of the day. It's not yours. You only have access to it through OpenAI, and you'll get charged by every time you query it. So there are other services, if you don't like what OpenAI has to offer, that are competitive in some aspects with OpenAI's tooling. Databricks has one called Dolly. AWS has one they announced just a couple of weeks ago called Bedrock. There are also cheap and free alternatives. One thing that I think we can expect in the next 6 months to a year is that the supremacy of OpenAI in this space will not last much longer. I think that there are ways that we will get other open source methods. Yeah, I can imagine an instance where you're seeing an ad every other query, for example, but the queries are just as high quality as OpenAI can provide. And I just have some, what I call my ethical laundry list that I'd like to bring up to you all. This idea of large language models creating high quality misinformation, potentially with false attribution. There's nothing saying you can't fine tune a model to disseminate misinformation. There are also ways we've talked about where one can violate the safeguards that are in place by OpenAI, or just by taking an open source model and training it to create violent or explicit content. There's nothing stopping someone from doing this, and it's certainly already being done. And I think that large language model overhype may end up leading to over-reliance. And I think it's worth talking about some of the perceived large language model capabilities versus what they're actually capable of. So for example, complex deductive reasoning. We've seen that they can, in some instances, carry out this complex deductive reasoning, but it's not a guarantee. And the way deductive reasoning works is if you make if you make a mistake at one step, it's going to trickle down and it's going to be an issue elsewhere. And then the perceived quality of some of the output results, I would just highlight that our outputs can't be trusted. And really, there's no future in which you can trust them 100% of the time. And I think that part of this also stems from unhelpful anthropomorphisms. So saying that the LLM thinks or knows or understands, I've been susceptible to this as well. I think in the artificial intelligence space, we are sometimes prone to using them. I try not to. And then I think that this over-reliance on large language models could be a real problem when we talk about aiding with medical diagnoses, spiritual or religious issues, legal or financial services, or interpersonal interactions like dating, for example. And then finally, there's this sort of problem on the horizon about easily automated attacks on cyber infrastructure that I've been especially concerned about along with some of my colleagues. And that's it. Let's take any questions you all have. Thank you so much for your attention.